Now, in the previous lecture we have proved the general theorem on Gaussian quadrature rules. We have shown that with n plus 1 points we can derive a formula of order 2n plus 1. In particular, we have chosen the weight function as w x is equal to 1, taken the Legendre polynomials as orthogonal polynomials, and then constructed the Gauss Legendre quadrature rules. Let us now take the next set of formulas called the Gauss Chebyshev formulas. They are called the Gauss Chebyshev formulas. Now, here again the basic interval that we shall consider will be -1 to 1. Therefore, given an interval a b, we shall reduce it to -1 to 1 by using the same linear transformation. So, if the given interval is a b, reduce a b to -1 to 1 using the linear transformation. This linear transformation we have derived it last time, we can use the same transformation. This transformation we have written it as x is equal to half of b minus a into t plus b plus a. Now, t takes the values -1 to 1 when x takes the values a and b. Now, the weight function for the case of the Gauss Chebyshev formulas is the following: weight function w x is 1 upon under root 1 minus x squared. The corresponding orthogonal polynomials, or the Chebyshev polynomials. Chebyshev polynomials t n plus 1 x, which are defined as cos of, we have defined it as cos of n plus 1 cos inverse of x. While discussing the approximation, we have taken the properties of the Legendre polynomials and the Chebyshev polynomials also, and the Chebyshev polynomial is defined as t n plus 1 x is cos n plus 1 cos inverse x. The orthogonal property of Chebyshev polynomials is that the Chebyshev polynomials are orthogonal with respect to the weight function 1 upon under root 1 minus x squared, that is your w x, t m x t n x dx is equal to 0 for m not equal to n. So, that is a definition of the orthogonal polynomial. It is orthogonal with respect to the weight function w x over the interval -1 to 1. So, this is the orthogonal property of the Chebyshev polynomials. Now, when once we have fixed our weight function and the corresponding Chebyshev polynomials, the remaining part is quite straightforward, in that we have to pick out our abscissas and weights and then write down the formula. So, let us write down what will be the abscissas in this case. Abscissas are obtained by setting t n plus 1 x is equal to 0. So, I can put this cos of n plus 1 cos inverse x is equal to 0. Now, this is cos of certain quantity is equal to 0. So, I can set it as cos of some 2 k plus 1 into pi by 2. Cosine of this quantity is 0, therefore, this is equal to this, k is equal to 0 1 2 n. There are n plus 1 zeros, this is a polynomial of degree n plus 1, this has got n plus 1 zeros, therefore, we are setting k is equal to 0 1 2 3 n, thereby I can get all these zeros from here. Now, if I compare these two, what I would get will be n plus 1 cos inverse x is equal to 2 k plus 1 into pi by 2. I am comparing the arguments of the two functions. Then bring n plus 1 to the right hand side and also cos inverse x to this side. Therefore, I will have x, now I can put suffix k, this is equal to cos of 2 k plus 1 pi by 2 into n plus 1. This is 2 k plus 1 into pi by 2 divided by n plus 1, and k of course as we have written above 0, 1, 2, 3 n. These are the n plus 1 zeros of this Chebyshev polynomial of order n plus 1. Therefore, in the general case this when once n is fixed, I can write down what are these zeros of this. I take k is equal to 0. So, I will get pi by 2 into n plus 1 as the first 0. I will get the next 0 as x 1 is equal to cos of this is 3 pi by 2 into n plus 1 and so on. So, I can now get all the zeros of this Chebyshev polynomial as this one. When once I get these abscissas, now I need the weights in the formulas. So, let us write down what is our weights. Weights are given by lambda k, and this we had shown earlier that this will be minus 1 to 1 of wx lkx dx, where lkx is the Lagrange fundamental polynomial built on this n plus 1 abscissas, and an alternative form also we have written it. We can write in terms of these orthogonal polynomials. So, that will be wx, we have earlier used as p n plus 1, but now it is t n plus 1 x divided by x minus x k into t n plus 1 prime x at x k of dx. So, these will be the weights of this formula. Now, when once the weights and the abscissars are known, then we can finally write down what is our formula. The formula is minus 1 to 1 f x w x f x dx, that is minus 1 to 1 f x upon under root of 1 minus x square dx is a weight function that we have introduced, and that is your lambda naught f of x naught plus lambda 1 f x 1 plus so on lambda n f of x n. So, this will be the formulas that we will have. We know that the order of this formula is 2 n plus 1, order of the formula is 2 n plus 1. Now, let us write down few formulas, 3 of them which are important, and we shall use them in the examples. Let us write down 1 point formula. In the case of 1 point formula, we have n is equal to 0. Therefore, the corresponding polynomial will be t 1, t 1 of x is equal to x, t 1 of x is x, and we need its 0. Therefore, the abscissa will be simply x 0 is equal to 0 by setting t 1 x is equal to 0. So, we put t 1 x of x is equal to 0, I get x 0 is equal to 0. I need the derivative here for the weight. So, let us write down differentiate this t 1 dash of x is equal to 1. So, its derivative is only 1. Therefore, lambda 0, let us put k is equal to 0 here. So, I will get here minus 1 to 1, the t 1 is x in the numerator, I am writing t 1, w x is under root of 1 minus x squared, w x 1 minus x square, x minus x k, therefore, I will have x minus 0, x k is 0, derivative is 1, this is simply dx. So, let us just simplify this. This is equal to minus 1 to 1, or simply dx upon 1 minus x squared, under root of this, and this is simply integrally sin inverse x. So, I can just 2 times I will write down 0 to 1. So, I can write it as sin inverse of x 0 to 1. That gives me 2 into pi by 2, sin inverse 0 is 0. So, I will get simply pi. Therefore, the 1 point formula is minus 1 to 1 f x upon under root of 1 minus x square dx is pi into f of 0. The abscissa is x 0 is 0 and we have lambda 0 is equal to pi. So, simply pi at x 0, which you can see that it is almost like a midpoint rule, at the middle point only it has been obtained, and the order of this formula is 1, that is your 2n plus 1. Therefore, n is 0. So, we will have the order of the formula as 1. Therefore, this will integrate polynomials of degree less than or equal to 1 exactly. So, let us derive a 2-point formula. Therefore, I need to take n is equal to 1. Therefore, I need 2x, which is we have derived it as 2x squared minus 1. Therefore, I can immediately write down the abscissas from here by setting t to x is equal to 0. Therefore, I would get here x square is equal to half. Therefore, x is equal to plus minus 1 upon root 2. So, let us choose our x 0 is minus 1 by root 2 and x 1 is 1 upon root 2. So, we choose the two abscissas as x 0 is minus 1 upon root 2 and x 1 is minus 1. Now, I need the expressions for lambdas. So, let us write down our lambda 0. Now, before doing that, let us do one more thing. T to x, as let us take 2 common out and write this whatever is left out as x minus x naught into x minus x 1, because easy then to cancel. So, I will write down t to s, 2 I will take common, and this is a factor of x minus x naught, x minus x 1. Therefore, I will have here minus 1 to 1, this is t 2 in the numerator, then the weight function 1 upon under root 1 minus x squared this into x minus x naught, and t 2 prime is 4 times x. Therefore, this will be 4 times at x 0 dx. Now, this will let us cancel off this x minus x naught, x minus x this one, and let us take x naught is constant. So, let us pull it out. So, it will be 1 upon 2 times x naught, and this is minus 1 to 1 x upon under root of 1 minus x square minus x 1 upon under root 1 minus x square. I just separated this x minus x 1, x divided by under root of 1 minus x squared minus x 1 upon under root of minus x squared. This is an odd function, therefore, the value of this is 0 between minus 1 to 1. So, this gives us a value, and let us take the constant out. This is minus x 1 upon twice x naught minus 1 to 1 dx upon under root of 1 minus x squared. Now, we have just now shown the value of minus 1 to 1 dx upon 1 minus x square is equal to pi. So, I can use this value as pi, and here the ratio of x 1 and x naught is minus 1. Therefore, ratio of x 1 upon x 1 is minus 1. So, we will have a plus half into pi. So, I will have simply pi by 2. Now, let us go to the next value lambda 1. Lambda 1 gives us minus 1 to 1 2 times x minus x naught x minus x 1, the weight function under root 1 minus x squared, the factor x minus x 1 into t 2 prime is again 4 times x at x 1, that is 4 times x 1 dx. Now, let us again simplify this. We will take this x 1 outside. So, I will have 2 times x 1 minus 1 to 1, again x upon under root 1 minus x squared, and this is we have cancelled this x minus x 1 and this x minus x 1. What is left out is x minus x naught. So, I will have x naught upon under root of 1 minus x squared dx. Now again this is an odd function, therefore the value of this is 0. So I again have this minus sign outside. So x naught minus 2 x 1 minus 1 to 1 dx upon under root of 1 minus x squared. Now this is same as this, because the ratio of x 1 by x naught and x naught minus x 1 is minus 1. So I will again have this as pi by 2. Therefore we are in a position to write down the formula. The formula is minus 1 to 1 f x upon under root 1 minus x squared dx is pi by 2 into f of minus 1 upon root 2 plus f of 1 upon root 2, and the order of the formula is 2n plus 1, that is equal to 3. The order of the formula is 3. So it is going to integrate exactly polynomials of degree less than or equal to 3. Again we can compare with the Simpson's rule, wherein we have 3 points and they are equispaced points, and here we have relaxed that condition, therefore we are able to get a higher order formula. Now let us derive one more formula before we take an example. Let me take the 3 point formula. Therefore I need to take n is equal to 2 and the polynomial is t3 of x, which is defined as 4x cubed minus 3x. N is equal to 2, therefore the Chebyshev polynomial of order 3, that is t3x, is 4x cubed minus 3x. Now I can again find the abscissas from here. I set t3x is equal to 0. So I would get here x into 4x squared minus 3 is equal to 0. So I have the value is 0, x is equal to plus minus root 3 by 2. Therefore we shall choose the points as x naught is minus root 3 by 2, x 1 is 0, x 2 is equal to root 3 by 2. And t3x we shall write this as, I will take common factor 4 out and then write the remaining as x minus x naught, x minus x 1 into x minus x 2. Let me illustrate the finding out one of the lambdas, the remaining I will give the values of them. Now let us write down lambda 0 that is minus 1 to 1, t3 that is 4 into x minus x naught, x minus x 1 that is 0, let us retain it as 0, x minus x 2 under root of 1 minus x squared into x minus x naught into, now I need the derivative of t3. So let us write down t3 dash x, that is 12 times x squared minus 3, this is 12 x squared minus 3. So that I can write it as 3 into 4 x squared minus 1. So I will this as 4 times x naught square minus 1. Now we will cancel off x minus x naught from here. Let us compute what is this value. This is 4 times x naught squared minus 1, x naught is minus root 3 by 2. So that is 3 by 4, that is 3 by 4 into 4, that is 3 minus 1, that is 2. So this value of 4 x naught square minus 1 is equal to 2. Now there is a 2 here and 4, let us take it out. So I will have here is 2 by 3, I have taken 2 by 3, and what is left out is minus 1 to 1. Now let us multiply it out, x squared upon under root 1 minus x square, I am combining these two, x square upon this minus x into x 2 upon under root 1 minus x square. I have taking this as 2 factors, x into x squared, and this is minus x into x 2. Now you can see that this is an odd function now, therefore the value of the second integral will be 0. So only the first integral is going to contribute, that is equal to 2 by 3 minus 1 to 1 x squared upon under root 1 minus x squared. It is an even function, so I can write this as 4 upon 3 0 to 1 x squared under root 1 minus x squared dx. So let us use your standard substitution, x is equal to sin theta, then we have dx is equal to cos theta d theta. So that this integral simplifies to 4 upon 3 theta is equal to 0, sin 0 is 0, x is 1, theta is equal to pi by 2, x square, that is sin square theta, dx is cos theta d theta, this is 1 minus cos square is sin square under root of this, that is sin of the cos of theta, 1 minus sin squared, we have cos squared under root of this cos theta. Therefore this is simply equal to 4 upon 3 0 to pi by 2 sin squared theta d theta. Now let us use the reduction formula, this is equal to 1 by 2 into pi by 2, 0 to pi by 2 sin squared theta 1 by 2 into pi by 2, therefore this is equal to pi by 3. Now let us write down lambda 1 also, because it is slightly different from this coefficient. So let us just write down what is our lambda 1. Lambda 1 is minus 1 to 1 4 times x minus x naught into x minus x 1 under root of 1 minus x squared, we have a x here, then 4x the T3 dash is 3 times 4x square minus 1 at x is equal to 0. So I will have a minus 3 coming from here, so I will have a minus 3 here and dx. Now this, therefore this gives us minus 4 by 3, now x cancels here, so I will have minus 1, and this product I will open it up as x squared upon under root 1 minus x squared, that is the first term, then I am multiplying it out, therefore we will have here x into x naught plus x 1, I am writing the product of these two, divided by under root of 1 minus x squared, then the product of these two is plus x naught x 1 by under root 1 minus x squared dx. So we will have 3 terms in this case. Now this is 0, this is an odd function, therefore the middle integral gives contribution is 0. So we will have contribution only from these two integrals, and this is even, this is even. So I can now write this as minus 8 by 3 0 to 1 x squared upon under root 1 minus x squared plus, now we have found out the values of x naught and x 1, x naught into x 1 x 2, we are using it as x 2, the middle one x 1 was 0. So x naught plus x 2, x naught into x 2 is the product of these two, that is minus 3 by 4. So we will have this as minus 3 by 4. So let us make this as minus 3 by 4 into under root of 1 minus x squared dx. Now these, both these integrals have been just been evaluated earlier, so we can you can simplify this, and I will give the value of this also as equal comes out to be pi by 3. We have evaluated the second integral while finding lambda 0, and the first integral was also evaluated earlier, lambda 1 comes out to be pi by 3. and now show that lambda 2 is also equal to pi by 3. Lambda 2 is also equal to pi by 3. Therefore, we will have the 3-point formula as f(x) upon under root 1 minus x square dx is pi divided by 3 f of minus root 3 by 2 plus f of 0 plus f of root 3 by 2, and the order of this formula is 5. Order of this formula is 5. Interestingly, it can be shown theoretically that in the general case all the lambdas are equal as it has happened here, and indeed in the general case lambda naught, lambda 1, they are all equal and they are all equal to pi upon n plus 1. In the case of 1-point formula n is equal to 0, we get the weight as pi. In the case of 2-point formula n is equal to 1, we get the weight as pi by 2. In the case of 3-point formula n is equal to 2, we get the weight as pi by 3, but in the general case we can show by integrating the Chebyshev polynomial, we can show that all the weights are equal and they are equal to pi by n plus 1. Now let us take an example. So let us say evaluate minus 1 to 1 minus x square to the power of 3 by 2 cos x dx using 2-point and 3-point Gauss Chebyshev formulas. Now before actual working out the problems, two things, important thing that you should note is whether the interval was given as minus 1 to 1. If it is not, we use the linear transformation, first reduces to minus 1 to 1. Secondly, given the particular formula, whether the suitable weight function is available or not. If the weight function is not available, we provide the weight function, that means multiply and divide by the weight function to produce the weight function for the formula to be used. In this example you can see that the weight function is not available for us, that is under root of 1 minus x square. So we divide by under root minus x square and multiply by under root 1 minus x square. So we shall first of all write this as minus 1 to 1. I have to divide by under root of 1 minus x square, which is the weight function I need. So I multiply by this. So I would have this numerator 1 minus x square whole square cos x dx. So I have now provided the weight function in the formula so that we can apply the Gauss-Chebyshev rule, and the limits of integration is minus 1 to 1. So we can apply the formula directly. Therefore I can recognize now my function f(x) as this is of the form f(x) upon under root of 1 minus x square. This is the Gauss-Chebyshev form. Therefore f(x) will be 1 minus x squared whole squared into cos x, 1 minus x square whole square into cos x. When once you recognize this, the application is really trivial. So let us write down our 2-point formula. The 2-point formula gives us I is equal to pi by 2 f of minus 1 upon root 2 plus f of 1 upon root 2. So let us substitute it pi by 2. So we just substitute this in the, you can see that it is, we have all even function completely. So for both the values going to be same. So we can do multiply 2 times straight, and this is 1 minus x square 1 minus 1 by 4 1 by 2 whole squared cos of 1 upon root 2. So this gives you 1 by 4. So this is pi by 4. This is simply pi by 4 cos of 1 upon root 2. I can evaluate this value and write this as 0.59709. Let us now use the 3-point formula. So, I can now write this as I is equal to pi by 3 f of minus root 3 by 2 plus f of 0 plus f of root 3 by 2. Therefore, we can evaluate them pi by 3 . We substitute minus root 3 by 2 here. So, we will have 1 minus 3 by 4 whole square cos of minus 3 by 2, f of 0 is 1, cos 0 is 1, that is 1, and this is 1 minus 3 by 4 whole squared cos of root 3 by 2. So, these two we can combine them and write this as pi by 3 2 times 1 by 16 cos of root 3 by 2 plus 1, and the value of this is 1.132. We can see that evaluation of the integral is not simple. With the 2-point formula we got the value as 0.597, and with 3-point formula we got the value as 1.132, because this is order 5, and in fact we are not sure whether this result is still correct. We still have to take a 4-point or 5-point formula to see the difference between them and find out what is the real result here, because you can see that even this simple problem turned out to be not that simple. It turned out to be quite difficult, that the convergence is not immediately seen. So, if I am able to show that the difference between these two values is a particular tolerance, then we can stop at that particular value. However, the most important thing here is the tables of all the Gaussian formulas are available up to 16 decimal places. That means the weights and abscissas are available for us in the standard tables for 16 decimal places. Therefore, even if you do in double precision the entire computation, you would not lose any accuracy, because we have shown that in all the integration rules the round off error is not having great effect. It at the most multiply by b minus a, that the length of the interval that we have taken. Therefore, if you retain 16 decimal places for both weights and abscissas, we can expect at least 12, 13, 14 places to be accurate in our result. Therefore, you can get the results of any accuracy, you can go to the any higher order formulas. As I said, it is available for any order in the tables. Now, let us go to the other type of formula, which is our improper integrals, which are also very important, and that is your 0 to infinity, minus infinity to infinity problems. So, let us look into those problems. We shall first consider the formula of the type 0 to infinity w x f x dx is lambda naught f x naught, lambda 1 f x 1, lambda n f x n. The first class of the formulas that we consider is where the weight function is w x is exponential of minus x. The reason is that the orthogonal polynomials are available for me which have the weight function exponential of minus x and orthogonal over 0 to infinity, and these are the solutions of the Lagari differential equation. They are called the Lagari orthogonal polynomials. As I mentioned earlier, these orthogonal polynomials are the solutions of the differential equations that belong to the Sturm-Liouville family, which are variable coefficient differential equations. For suitable expressions for the coefficients of y double prime, y prime and y, we get Legendre's differential equation Chebyshev differential equation, Lagari differential equation and Hermite differential equation. Now, since these are variable coefficient differential equations, the solution is obtained in a series form by the Frobenius method. The solution of these differential equations lead to orthogonal polynomials. The solution of Legendre's differential equation gives Legendre polynomials. The solution of Chebyshev differential equation gives Chebyshev polynomials. The solution of the Lagari differential equation gives Lagari polynomials, and the solution of Hermite differential equation gives Hermite polynomials. So, based on this, what we really require is called the Gauss-Lagari rules or formulas. Gauss-Lagari rules. The weight function in this case is exponential of minus x, exponential of minus x. That means what we are looking for is an integration rule for 0 to infinity e to the power of minus x f x dx is equal to lambda 0 f x 0 plus so on lambda n f x n. As in the case of the Chebyshev polynomials, if this weight function was not available for us in a given problem, we shall supply the weight function, that is multiply by exponential of minus x divide by exponential of minus x. That means, if suppose you are given only a problem as gx dx, then what I would write it here is I will write this as e to the power of minus x into e to the power of x gx dx. This will be my f x. This will be my f x. So, even if the weight function is not available for us, we shall provide the weight function and then get this formula. Well, now I need the set of orthogonal polynomials for this. Orthogonal polynomials are called the Lagari polynomials. They are called the Lagari polynomials, denoted by L n plus 1 of x. The definition of Lagari polynomial, it can also be put in closed form as we are able to do with Chebyshev polynomials. So, we define it as this: minus 1 to the power of n plus 1 exponential of x d n plus 1 upon this e to the power of minus x to the power of n plus 1. It is analogous to the Rodrigues formula for Legendre polynomials with L0 is equal to 1, where L0 defined as 1. Therefore, the orthogonal property of this should be 0 to infinity exponential of minus x L m x L n x dx is 0. So, this is the orthogonal property of the Lagari polynomials. Let us now find few of the Lagari polynomials. Now, set n is equal to 0 in this equation, then we get L1 here minus 1 to the power of 1, therefore, a negative sign, n is 0, therefore, is a first derivative, n is 0, I will have here x here. Therefore, I will say set n is equal to 0, then I will have L1x is equal to minus exponential of x d by dx exponential of minus x into x. Now, I can differentiate it and get minus e to the power of x. It is a product of two functions. So, I can differentiate it. I will get minus e to the power of minus x into x plus e to the power of minus x. That will be equal to x minus 1. I have absorbed the minus sign inside. This gives me the first Lagari polynomial. Now, set n is equal to 1 in this equation to get the Lagari polynomial L2x. Therefore, when I set n is equal to 1, I get here minus 1 whole square is a positive sign. This is the second derivative and I will have here x square. Therefore, L2x will be equal to exponential of x d square upon dx squared e to the power of minus x into x squared. Now, again I will differentiate it as a product. Therefore, I will get here e to the power of x d upon dx minus e to the power of minus x x squared plus e to the power of minus x into 2x. Again I differentiate it. Therefore, I will get here e to the power of x. Now, minus minus becomes plus e to the power of x x squared. Then I have minus 2x into 2x. This is again minus e to the power of minus x into 2x. I differentiate it, I will get 2 from here. So, e to the power of minus x into 2. Now, let us simplify it. E to the power of minus x cancels e to the power of x. This is x square, this is minus 2x, this is minus 2x. Therefore, that gives us minus 4x and this gives us 2. Therefore, I will have this as x squared minus 4x plus 2. Therefore, the Lagari polynomial L2x is given by x squared minus 4x plus 2. Now, set n is equal to 2, I will get the Lagari polynomial L3x. That will give me minus e to the power of x d cubed upon dx cubed e to the power of minus x into x cubed. Now, I will leave this derivation for you. This value comes out to be x cubed minus 9x squared plus 18x minus 6. Therefore, in the integration rule we substitute the zeros of the Lagari polynomials and then write down the required formula. Therefore, the abscissas in the integration rule, abscissas in the integration rule are given by the zeros of L n plus 1 x dx, L plus 1 x is equal to 0, and the weights are given by lambda k is 0 to infinity, the weight function e to the power of minus x L n plus 1 x divided by x minus x k L n plus 1 prime of x dx. The abscissas are zeros of L n plus 1 x. We have derived the expressions for L1x, L2x and L3x from which their zeros can be obtained. The weights are given by the corresponding lambda k. Let us get two rules and then take an example. Let us take 1 point rule. So, we will have n is equal to 0 and L1x is equal to x minus 1. Therefore, there is only one abscissa, the abscissa is x0 is equal to 1. Now, we need the derivative here. So, let us differentiate, that is 1. Therefore, lambda 0 0 to infinity e to the power of minus x, this is x minus 1, x minus x k, that is x minus 1 into derivative is 1, derivative is 1 and this is x minus 1, ln plus 1 is x minus 1, the leading coefficient is only 1 here. So, this is integral e to the power of minus x dx and minus e to the power minus x 0 to infinity. So, it will give you simply 1. So, the value of this is 1. Therefore, our 1 point rule gives us 0 to infinity e to the power of minus x f x dx is equal to simply f of 1. This is order of 1. It is simply evaluated f at 1. Now, let us take the 2 point rule. N is equal to 1. So, we will have L2x is equal to x squared minus 4x plus 2. Therefore, let us put L2x 0 and get our abscissas. So, we will get abscissas as x squared minus 4x plus 2 is equal to 0. So, we will have x is equal to 4 plus minus b squared minus 4ac by 2. So, that gives us 2 plus minus, this is 8 2 root 2. So, we will have 2 plus minus root 2. Therefore, the two abscissas are 2 minus root 2 and x 1 is 2 plus root 2. And L2x, again leading coefficient is 1, simply I can write it as x minus x naught into x minus x 1, x minus x naught into x minus x 1, and we need its derivative. L2 dash is 2x minus 4, 2x minus 4 or 2 into x minus 2 I can add it. Therefore, let us find out lambda 0, 0 to infinity exponential of minus x. Let us reduce one step, x minus x naught comes in the denominator. So, let us cancel off that. So, x minus x 1. So, I have cancelled off x minus x naught, and what is left out is your L2 dash at x k. So, L2 dashed at x 0, x 0 is 2 minus root 2. So, I will have here is 2 minus root 2 minus 2. So, that will be simply minus 2 root 2, 2 to cancels off, and I will have minus 2 root 2. So, I will have here minus 2 root 2 of dx. Therefore, this gives me minus 1 upon 2 root 2. Now, let us integrate it as a product. So, this we will have this as integral of this as x minus x 1, x minus x 1 minus integral of, there is a minus minus plus. So, I will have integral of e to the power of minus x dx. We will put 0 to infinity in a moment. I just integrated by parts. So, e to the power of minus x with a negative sign into this plus e to the power of minus x, derivative of this as 1. So, this is minus 1 upon 2 root 2 minus e to the power of minus x, x minus x 1 minus e to the power of minus x, 0 to infinity. At infinity both of them are zeros, and at the lower limit we will have the, we will have here 1 upon 2 root 2, this is a plus sign. So, the minus x 1 I will have, and this is plus 1 at the lower limit. So, x 1 is, we have it here 2 plus root 2 and this is a plus 1. So, what we have here is minus 1 upon 2 root 2, this is minus 1 plus root 2. I will write down one more step, 1 upon 2 root 2 into root 2 minus 1. I have taken the minus sign inside, and let us remove this root 2 from the denominator. So, I will multiply that, that is 2 minus root 2 by 2 into 2. Minus x 1 plus 1. So, yes, minus, yes, minus 1 minus root 2, minus 1, you are right, minus 1 minus root 2, correct, is minus 1 minus root 2, that is root 2 plus 1, 2 plus root 2, that is 2 plus root 2 by 4. Now, I will leave the second one to you to do this. This is comes out to be 2 minus root 2 by 4. Therefore, our 2 point rule is 0 to infinity e to the power minus x f x dx is equal to 1 upon 4. I will take this 1 upon 4 outside. The lambda 0 is 2 plus root 2. I have written 4 outside, and the abscissa corresponding to this is the first abscissa 2 minus root 2, and the second one is 2 minus root 2, and the abscissa is 2 plus root 2. 4 I have written outside. So, this formula 2 point formula is very easy to remember, that this particular argument that we have goes as the argument of this, and this argument comes as this. So, these numbers are same, these numbers are same, and this is of order 3. As I mentioned, all the weights and abscissas for this Gauss-Lagari formula also are available in tables up to 16 decimal places, and whenever the weight function is not available, we shall provide the weight function and then construct the solution problem. Okay, we will stop it.